Good morning to all of you. Uh, so today we are going to deal with a very interesting aspect of NMR spectroscopy, but that is typically observed in trigonal bipyramidal structures such as the compounds of phosphorus or any other complexes like FeCO5. So any trigonal bipyramidal structure shows a very unexpected and very different kind of behavior in NMR, and that is something attributed. That is the reason being that it has rapid rotations occur in that, which is very it changes the symmetry of the system, and that's why you get and that happens at a very faster rate, which is called very pseudo rotation. So what happens is that NMR spectroscopy, the way we have just dealt with, we now know both the techniques, that is a continuous waves uh, spectrometer, which has a constant, there's a constant irradiation with a radio wave for entire period of the scanning that we do. And there is this one that we just talked about in few days back, that was the pulse technique. You have a short pulse of microsecond duration, and then that is the pulse profile changes. If it is some of the waves are absorbed, the pulse profile will change, and that we analyze in the way that I told you. We applies the coils, detection coil, and all that. So that was using and the radio frequency that we use is now circularly polarized. So that was the techniques, two techniques that we uh, uh, NMR spectroscopy can be conducted in two different ways: continuous CW or FT, the Fourier transformation with a pulse, using a pulse. So even by both techniques, even if we refer to this, NMR spectroscopy is always thought to be, it is considered to be a slow spectroscopy technique as compared to others such as FTIR spectroscopy, infrared, the FTIR that we do, or uh, absorption, fluorescence. All these are the events that happen. Is the spectroscopy captures the events at which is happening at 10 to the power minus 15 minus 12, so picosecond or femtosecond order. But here the NMR spectroscopy, when you are trying to do that, it happens the data acquisition usually takes place at around microseconds, few microseconds. That we saw that the pulse that if we try to calculate the pulse uh, duration by the formula that I gave you yesterday, gamma being 1 by that one. So it turns out to be a few microseconds. So that is your data acquisition time. That much time you have to invest. And if something is happening much faster than that, if if something happens, say about 10 to the power minus 12 seconds order, picosecond order, then that thing you won't be able to detect in NMR, because that motion will be so fast that you will get only an average picture. Okay, so what you get is that in NMR you will get a time averaged picture, which will not be able to know the finer difference of the geometry or anything like that. So this is typically you will observe in PF5 or any other such things. So if you remember earlier also, I talked about this in first semester during the ligand substitution reactions. I had talked about Berry pseudo rotation that happens. So this was the thing that we discussed earlier in the first semester. So see this picture, it is very clearly illustrates what happens to so this is a trigonal bipyramidal geometry, the picture A. So look at this. I need all your attention on this picture. So you see here the equatorial plane, the triangle that you see here, this is the position, this is the position of this So these are the three things that you can see. This triangle is, you can picture it like all these three are lying on this trigonal plane, right? And the two other ligands, two other substituents, one is here, these are equatorial, right? Equatorial, sorry, this is the axial, oh sorry, this is axial along the axis, and these are equatorial, right? Equatorial plane, right? So this equatorial plane, this forms if you connect the dots, it forms a triangle, right? So this is the what we is represented here, sorry. So this is the axial and equatorial, this is what we know. Now suppose the movement that will happen is like, when we talk about rotation, this rotation happens very fast, and the steps that you can imagine that happen, that takes place, is like these two, the green one, the yellow one, these two, with the yellow arrow, look at them, they will move along the direction of the arrow, and what you will get is the second picture, B. So this, now see this, the green one has moved in the direction towards the left, and now the green and the yellow are now aligned. And you see that if you look very carefully, this one, these four are in one plane. So this is a square, it forms a square in one plane. Connect the dots, and it is a square like thing that is formed in one plane. And this is the pyramid that we are talking about, square pyramid, okay? Square pyramidal structure. And then the movement, this is a just intermediate position in the middle of the motion, that is the rotation that is happening. It is in the, we are in the middle of that motion, and the next movement is that of the other that we, so can you imagine this, the triangle, this was the triangle, the two move out, and we are now having a square, and square, this is the apex of this is a square pyramid. Can you see this square pyramid, right? So something that was so, and then the next, so it is still moving, the molecule, the motion of the bonds in relation to the other is taking place, and now this is it, these two will move towards the inverse in this direction, okay? So what happens, they will finally be here like this. So now you see the triangle has changed. Now these three things are now uh, in one plane, okay? So this is the triangle, and above it is the green one is coming out of the plane of the screen, and the yellow one is behind the plane of the screen. So this is the kind of situation that you have in the third picture. So now see, initially this was axial, this was also axial, and now these were equatorial. In the final picture in C, you will see that now that has changed. Now these three are in one plane, the triangular plane that you are viewing. Connect the center to center of this. So this is forming one triangle, and the axial, something that was equatorial has now become axial. So this is the axial. These two are axial, and these three are equatorial now. So the distinction between the axial and equatorial is gone. Earlier you have learned that in a trigonal bipyramidal geometry, the equatorial bonds are shorter, axial bonds are longer, right? So based on that, the environment of the around the nuclei would be different, and we should get if in a static condition. If you are imagine a trigonal bipyramidal geometry in a static condition, सब कुछ रुका हुआ, stopped. In that case, two long bonds, three short bonds would be there, and because of that, if though they happen to have a magnetically active nuclei, then we should get different signals for the equatorial nuclei at the having the equatorial bonds connected by equatorial bonds, and another signal for the axial nuclei connected through the bonds to the central atom, right? But because this process happens so fast that initially this very pseudo rotation that occurs in the molecules such as this is so fast, and it happens at a time scale which is much faster than the data acquisition time for NMR, that you do not get to see any difference between the axial and equatorial nucleus, the signal coming from the axial and equatorial nuclei positioned over there. So this is something that are you getting the picture? You can see here that something this which was axial, these two were axial. Look at this, this was axial, this was axial. Now they have become this red and blue have now become, at this picture towards the right hand side, see, they have become the equatorial position, and something which was equatorial, that the yellow and green are now have become axial in the final picture. So there is a randomization that occurs. If you are taking time average picture, then all of them would behave as you will get that all the bond lengths are equal, something, everything is the electronic environment is that kind of picture will emerge. Okay, so because of this reason, so taken together, this is the movement that happens in a very fast manner, and that's why if you conduct NMR, for example, this is the example of FeCO5 13C NMR. If you conduct, instead of getting different signals, you only get to see uh, you do not get different signals for axial or equatorial carbons in 13C NMR, because there is such a fast change in structure. The rotation is happening fast enough. The equatorial one becomes axial in the next moment you are observing them. So this happens very fast, and the data acquisition for 13C NMR is it's the instrumentation and everything is much slower, and this is happening very much faster than that, and so we are not able to capture it in the NMR spectrum. So this kind of thing happens. So this is what we are going to discuss today. This was just a visualization of the very pseudo rotation, and that's what we are going to discuss in slightly more detail, and how the spectrum will be changed behavior. So we will discuss some of the spectra, NMR spectra of such molecules. So what will happen in PF5? So in FeCO5 you will get one signal for all the carbons, all 13C NMR. In PF5, Fe is this phosphorus is also magnetic active, 31P. 31P is active. Fluorine 19 is also active, magnetically active. So there will be interaction. So there will be a splitting of the lines that will happen, as we discussed earlier, the fine structure in MR due to the interaction, spin-spin coupling. So that will happen, and what you should, so this is the picture of a trigonal bipyramidal geometry, typically of PF5 in a static condition, and we can imagine two different environments for the axial and equatorial. The blue one is equatorial, this is axial, and these are equatorial. This is how you visualize it. Two different environment is visualized, and so we should get two different signals, at least one for this kind, but we do not get it in PF5 because the movement that happens. So this is the first part of movement that we talked about, axial fluorine atoms. and then they start moving. So the axial ones start moving, and finally uh, so you have a square pyramidal type intermediate, and then finally the two equatorial ones become axial. Now these two are now axial, axial, and this one has become equatorial. So you can see this picture. So this is now equatorial. So this is the movement that happens. Orange substances are now equatorial. This rapid oscillation, this is rotation, which is known as very pseudo-rotation, affects the signals. So if you are observing a 31p NMR of the spectrum, so there are two things that you can, in PF5, there are two. Phosphorus is also magnetically active, fluorine is also magnetically active. So you can perform either 31p NMR, you can also perform 19f NMR. Okay? So if you are performing 31p NMR, if you are recording a 31p NMR spectrum, then all the 5 fluorine are equivalent. So so you can, just like you have drawn for the CH2 CH3, when the interaction of one proton, how does the splitting happens. So in a similar fashion you can go on. So AX2 AX3 AX5, AX3 4 5, so AX5 type situation. So in this case you will be having AX5 type situations. So the signal of A will be affected by presence of 5 different types. So you will obtain a sextet. 6. The 31 piece signal will be split into, due to the coupling and the scheme that we have discussed earlier. All are spin half nuclei. So the splitting pattern that we discussed earlier in the class will be based on. So you will obtain. So in case of a PF5 31 PNMR, patterns of coupling. So it will follow this Pascal triangles, 1 2 3 4 5. So if you go on extending, so you will obtain a sextet, this one 6. So 1 2 3 A AX AX1 AX2, sorry, AX3 AX4 AX5. So when we are talking about, so remember, if we are having a situation of AX5, 1 2 3 4 5 6, you should obtain a 6. So 31p NMR spectrum of PF5 should give sextet. Sextet because you are interacting with all having the 5 fluorine atoms which are attached to the phosphorus are all behaving in the same manner. They the distinction of the different bond lengths and different electronic environment is gone because of the Berry pseudo rotation that is happening. We just discussed that part, and because of that you will only obtain a sextet. Okay, because of this kind of interaction. So 5 different, so 5 fluorines which will, so due to the spin coupling, spin coupling, it will be split. The 31p signal, one signal split into 6. So that's the signal that you will obtain if you perform px5 NMR. Just a moment, कहाँ गए? Sorry. So this was the point that I was trying to, yeah, one more point. So this is what I was trying to explain. Yeah. So if you understand the fine structures very well, you should be able to predict. This is what is expected, and this is what you should expect in the examination, right? Okay, you should be now confident enough to predict any such spectrum, how many what the fine structure of the spectrum will look like. Okay, so a 31p NMR would give you a sextet in PF5, because the interaction, the coupling with all these 5 fluorine is of the same type. They are at the same time average picture is that all are equivalent. The distinction between axial and equatorial fluorine is gone. Okay, so that's why we get something like this. Okay, uh, molecule is in motion, we discussed already, 6 square with square pyramidal intermediate, and then axial, so swapping over of the positions are there, and this is also where is that? Oops. Oh, this is coming later. So this is the thing that happens, visualized together. So you can see something which at the start of the motion, something which was axial is now becoming equatorial gradually. The three, so because of this, you do not see. So now you can think of a 19F NMR and you can tell me what will it look like. So the fluorine, if you are performing 19F NMR, then how should the signal split? You can, this is, I will not tell, you should be able to tell this, what the fine structure will look like. So this is something that you should know. So if you are conducting 19F NMR, how should the spectrum look like? Question open, think over it. Okay, so 19F NMR would, so all the 5 fluorines are of the same type because of pseudo-rotation now, and they will have spin coupling. So if they are equivalent, they will have same Larmor frequency. They will appear at the in an isolated form. If there is no phosphorus present, all these fluorines will appear at one position in the NMR spectrum. Now because of the interaction with the phosphorus nucleus, this signal will split. It will split into a doublet. So because it is a phosphorus is also, so P is also spin half nucleus, F is also spin half nucleus. Okay, so your so that way, so a set of equivalent fluorine atoms, fluorine nuclei, are interacting with phosphorus, one phosphorus. So so spin coupling with the phosphorus, one phosphorus will give you a doublet, right? So a 19F spectrum NMR will be a doublet. Okay. So now we have already learned that FA and FE is a faster. So rotation is happening much faster time scale as compared to the NMR spectroscopy. The data acquisition of in NMR, it takes microseconds time scale. Pseudo rotation happening from nano to picosecond order, and so you are at least slower by 1,000 times slower than the what the speed of these things are happening. So this is, I think now you are getting it. PF5, if you are having so so this is the similar thing that we have discussed earlier in case of I may just discard it and show. Yeah, we discussed this point. So fluorine, if you are looking at 19F spectrum, then I told you that situation to be discussed here. Where was that? Okay, yeah, this is the situation that we are talking about. If you are looking at the X resonance and number of X increases with so this is the situation. The signal will increase when you are comparing AX and AX2. So this is the kind of thing, 1 fluorine or 5 fluorines. All are equivalent fluorines appearing at the same position, so the signal will increase, but they will appear at the, so this is, keep here, imagine the X is fluorine, 1 2 3 4 5. So AX2 you had increase in signal. If you have AX3, AX4, AX5, the signal will go on increasing. So AX5 will have a much higher signal, but at the same position. So this is what you have to remember, understand basically, that when I am asking you two questions, PF5, how will a 13p NMR spectrum will look like? How many lines you will observe? Then the second question, what kind of spectrum for the 19F spectrum? The fluorine is. So this is the situation that you are checking for the X resonance at one time, and which is affected by A. In other case, it is the A resonance which is affected by X. Okay, so the PF5, imagine PF5. So this is the situation when you are looking at F fluorine. All fluorine are equivalent due to pseudo-rotation, very pseudo-rotation that's happening. So they should appear at the same position, only the intensity will go on increasing if we are looking at the 19F spectrum. And and because they are interacting with the coupling is happening with only one nucleus of 31p, we should able to see a doublet with great higher intensity. Okay, but when you are looking at this thing, the resonance the NMR frequency signal for the A, that is in this particular case A is P phosphorus. If you are looking at the 13p 31p, so 31p spectrum, then A will be affected by each one of these interactions with one fluorine number 1, fluorine number 2, fluorine number 3, fluorine number 5. All these fluorine are equivalent, but so one interaction splits into two, another splits into another two, and they coincide, and this pattern we go on increasing, so we get this kind of Pascal triangle like things, and so if you get a sextet. So PF5, I think the pattern should be clear what is happening here. We have already discussed these patterns, and it is only the time that we are applying those concepts in understanding this kind of geometries which have geometrical features that we have. So PF5 is a good example for that understanding, developing that kind of understanding. Okay, and similarly you can think of any other TBP, trigonal bipyramidal, uh, any molecule having this kind of geometry that will be affected by these considerations, that is pseudo rotations, making all the positions equivalent, axial and and so, and then the splitting pattern you will analyze and observe like this. So look at the ClF3. So I told you that this rotation is happening very fast. So that is the case at normally at room temperature you won't be able to see anything different. But if you reduce the temperature, then the rotation will slow down at certain very low temperature. It is possible that rotation will stop. By knowledge of quantum mechanics, in rotations you can have J is equal to 0 can be populated, and J is equal to 0 means the quantum, that means that rotation, there is no rotation at all. So that kind of situation is acceptable. That happens in the molecules when you reduce the temperature at some 60 degree to minus 60 degrees. So this is example of ClF3. ClF3 molecule is having two lone pairs in the equatorial plane, one fluorine in the equatorial, and so initially, at when you if it is the spectrum is taken as 60 degrees Celsius, you get a singlet. All the three fluorines are equivalent. So nothing, and Cl. So this is the situation that that you see. But if you lower down the temperature, then they become distinguishable. The equatorial fluorine is affected by fluorine number 1 coupling with this, so split into 2, and then again second fluorine, so split into 3, so a triplet will be obtained. So you see fluorine, so this is the axial, axial, and this is the equatorial. So you also expect the signal, the integrated intensity of the axial one would be higher than this. So all these features you can analyze and you can find this is to be true, truly happening here. So there are two things. So these are the axial ones for the axial F, and this signal, the triplet that you obtain is for triplet is obtained for the equatorial. Okay, so this F, this is the fluorine nucleus, which is different from this, this is having different environment, axial ones, and so this splitting that you are seeing is the JFF FF equatorial with axial, right? So splitting, you have already noted this pattern. So F axial alone, sorry, equatorial, and then F equatorial interacting with F axial, splits into 2. Then further you have these two appearing at the same point. So now they are one. So this is the J that we are talking about, FF. Then you have another interaction, so FEQ, FAX, and then another one, F एक और जो दूसरा एक्सियल है 1, and this is the second, and so together you get 1:2:1. So this is the happening for the equatorial one. Now if you are thinking of in term from the point of view of axial, there are two of them, but they are similar, they are in similar. Two axial fluorines have similar environments, so that is, and they are only coupling with the one. Two F axials are equivalent, so the signal will appear at the same position, and when they interact with the equatorial one, they will be doublet. So you will see nothing like, so only you will see the signal of two. So in isolation, if you are viewing it, let me start it again. So thinking of 2F axial, if there is nothing appearing, only one signal will be there for the two fluorine atom axial, one signal. Now because they are equivalent environment, okay, there is no change, and so one signal, and then this 2FAX which were appearing at one position, they now interact with the one fluorine which is equivalent, which is equatorial position. So this signal will now split into 2 due to this interaction, and so you will obtain a doublet. Okay, so this is how you have to interpret. So in case of ClF3, you get at normal temperatures, you will get a singlet, and if they are if you reduce the temperature sufficiently, make it sufficiently low, then the Berry pseudo-rotation will stop at some point, and you will get to see the effect of different environments of the fluorine nucleus because of the different bonding situations, different bond lengths, right? So ClF3, it is a good example of this. that you can stop the very pseudo-rotation at -60, and the 19F NMR spectrum shows a doublet, one doublet for the two axial fluorine atoms and one triplet for one equatorial fluorine atom. FeCO5 we have, yes, in this case the rotation 13C NMR you can conduct. There is no proton, so a proton or is the magnetically active nuclei is C13. So if you enrich the carbon, the CO molecules with 13C, then you can usually you can perform 13C NMR, and you will find that here is a point to be noted, that 13C NMR will give you only a singlet, because there is a due to the very pseudo rotation there is a fast exchange, and because of that you won't see anything. So but if you perform, so this is the difference that I was trying to point out. Now you know FTIR, you also know NMR. So if you conduct FTIR spectroscopy on FeCO5, you get two types of signal, because the bond lengths are different, axial and so in FTIR spectroscopy you are getting that difference, because the FTIR spectroscopy is much faster event. Data acquisition in FTIR spectroscopy is done at that from picosecond to nanosecond order. It is very fast, and it is able to capture the vibrations that is occurring at at that time scale, uh, picosecond scales. Okay, so you are able to match up with the event that is happening, and your data acquisition time both are matching. So you will be able to capture that thing, because rotation is, before the rotation happens, rotation is completed, you are able to complete your data acquisition, you are getting the signal, acquiring the signal. And so in FTIR you will clearly see the difference. Spectrum will tell you that there is two different bond lengths, that FeCO one and the intensity of those FTIR bands will also be different, because one equatorial position there are 3 CO molecules, and axial position there are 2 CO molecules, and so the axial ones are longer, and so according the FEC bond lengths will be affected. So CO bond length, so because so this also we have discussed in metal carbonyls IR bonding situations. So because of that, you so this is a point that sometimes NMR will miss out on certain key aspects if you do it normally, and FTIR will able to tell you the difference in the molecule. So it is important that at what time scale you are performing the situation, are you matching up with the molecular event that is taking place. Data acquisition time must match if you want to see any difference. So 13 CNMR conducted, if you conduct at room temperature, we will see only one signal, indicating that all the CO atoms are having similar environment. But if you conduct FTIR at that also at room temperature, you will clearly see the equatorial and axial vibrations, the vibration of the which are appear at different frequencies. Okay, so that is something, yeah, so that is something important. In a similar fashion you can go analyze more such molecules. So next one is the SF4, sulfur tetrafluoride. So you can think of so this is also adopts a trigonal bipyramidal geometry. You can see this. So you have axial, 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 and two axial fluorines and equatorial, two equatorial fluorine atoms. So the environment is different, but if you conduct the NMR at room temperature, then 23 degrees Celsius you are getting only one sulfur. So here you see you are getting So there's one more difference that you can see here. You are getting a singlet. PF5 you were getting a doublet, right? So the difference being that here the central atom, the sulfur, is non-magnetically inactive. Sulfur, the normal isotope that we have, sulfur 32 is S32 is 32S is not magnetically active. So you have no interaction with the central atom, the nucleus of the central atom. So all fluorine are equivalent, they will appear due to this pseudo rotation, and so they appear at one, they all have same Larmor frequency, they appear at the same position on the chemical shift scale. On the NMR, in the NMR spectrum, you plot chemical shift on the x-axis and they appear at one position because they all have one Larmor frequencies which remains unaffected. So corresponding to each one of them. So this is the normal case at room temperature. If you slow it down, if you reduce the temperature -100, then the rotation will stop. Rotation stops, and you can see the distinction that two axial are having one type of environment, another two having a different type of environment. So they should appear at different positions. They should appear at different position in the NMR spectrum. And what will be the spin-spin coupling? What do you affect the fine structure would be? So two axials. So again, so two fluorine axials. So they appear at have same Larmor frequency, appear at same position. Now they will interact with one by one. F equatorial number one. So they will be splitting in two. Then in the next, you can consider it is also interacting with, after one, it is also interacting with F equatorial number 2, and so there will be further splitting of these lines into, so appearing at the same position. So you will have a triplet 1 2 1, right? So this kind of thing will happen. So this is what this, so in a similar fashion you can think of the equatorial positions. The two equatorial fluorines are under the same environment, they have same Larmor frequency, so they will appear at the same position. Now when they interact with one axial, they split into two. When they interact with the second axial rule, so the coupling, spin-spin coupling, will give rise to 1:2:1. So two triplets are observed for SF4 because of that kind of interaction. So do you understand? So do you understand this? The two axials, this, this, they both will have same Larmor frequency at low temperature. And then if you look at the other one, the two equatorial, this and this, both will have same Larmor frequency. Okay, and then now this interact with, so appearing starting from the appearance in isolated thing, if there is no different nucleus, they will appear as one. But when they interact with axial number 1, axial number 2, the splitting will happen due to the spin-spin coupling, and you will obtain a triplet, the pattern which we discussed earlier. So this kind of situation, yeah. So SF4 you are getting due to this. So 19F, so this is the 19F NMR, of course, because you have to define your system, the instrument, the probe, everything will change whether you are performing 19F NMR, the or proton NMR, things like that. So in a similar, so this is the, so when we are talking about PF5 or something, it is also important to note that if you have a static, so in a static condition, if you are analyzing the molecule, rigid molecule, trigonal bipyramid, then, so taking example of PF5, if suppose you are doing at low temperatures, then what we understand as that the PF, the splitting of P and F, the coupling is much stronger. So they split. So first, so you take the fluorine, axial fluorine, fluorine axial, and so the first interaction that you take is with P, with, phosphorus, spin coupling, which is much stronger. So the splitting is much larger. Splitting is larger. JPF, what we see that JPF is much larger than JFF. So in such cases, when you have to find the pattern, you, if something is having a larger one, you take into account first. Okay, so draw that first and then do the next. That makes it easier. Okay, so if the fluorine coupling is smaller, so you see the splitting will be less. So first splitting is you obtain is larger, JPF. Okay, after that you the interaction with happens with the, sorry, the next set of interaction, the fluorine interaction, and that splitting pattern you will observe. So if you are considering a rigid, so there are two axial fluorine atoms which are, so they are equivalent, they are interacting with three others, three equatorial fluorines. So there will be splitting will occur in, you will obtain a quartet, and that will appear. So JFF, so this F axial, two F axial one interacts with F equatorial number 1, F equatorial number 2, F equatorial number 3. So splitting will occur at each stage, and finally you will obtain a quartet. Splitting pattern will give you, so quartet will be obtained. Okay, so this is the way you will find, and because this first splitting was very large, JPF, so there will be two quartet for axial like this. Then again for equatorial one, so overall you are obtaining these many lines, two quartets separated by such a large thing. Uh, so JPF and JFF, so this is the JFF, smaller, much smaller than, so the actual order is around 100 and 1000, something like that, it hertz. So similarly you can define for equatorial. So so you have three equatorial fluorine. Okay, and this interacts with one fluorine axial 1. It will also interact, then you can interaction with F axial 2. So there will be 1:2:1, 3, you will obtain a triplet. Okay, so this will happen in a rigid system. If somehow we are making by lowering the temperature, that is one way, making it rigid. There's another way, like you have a bulky substituent, that will also make it rigid, and rotation will be hindered. In such cases you will, like, you will have a situation like this emerging. So the example that to illustrate this example, and illustrate this concept, I'm taking example of PCl2F3 here. PCl2F3, so 2Cl lying in the equatorial, the apicophilicity, you have already learned that in first semester. So fluorine takes the apex position. So this is there are two things pictured over here. One is the PCl2F3 under normal conditions, above, at -22 or above, you will obtain a doublet which will represent only, so JPF, so so this is pseudo rotation happening, pseudo sorry rotation is taking place, and because of that there is no distinction between equatorial and this position. And so whatever you are obtaining is simply the set of three fluorine atoms which are non-distinguishable. Their spins is splitting by interaction with the phosphorus, so you are obtaining only a doublet, right? Pseudo rotation हो रहा है. Pseudo rotation की वजह से there is all the three fluorine nuclei will appear. There is no distinction between them because the equatorial becomes axial becomes equatorial during the rotation, and so you will obtain only one signal in isolated condition for the three fluorine. But because phosphorus is the central atom to which all of them are connected, and so there will be interaction which is also magnetically active, the splitting of there will be, so they will be it will split into two, a doublet will be obtained. So at temperatures greater than or equal to, equal to minus 22 degrees Celsius, this is the situation. If temperature is greater than minus 22 degrees, so even if you conduct at room temperature, this will be the situation, a doublet. And the doublet, the separation between the doublet is very huge. So this is J. Look at this coupling constant, which is very high, 1048. Now if you reduce this thing, temperature is reduced to minus 143, then the rotation stops. Pseudo rotation is pseudo rotation stops at minus 143. So minus 43 degrees Celsius, the pseudo rotation stops. So you have two different things that you can imagine now. One, so pseudo rotation has stopped here, and so the equatorial one will give one signal, the axial one will give different signal because of the difference in Larmor frequencies. Now you consider the interactions of the fluorine with the other fluorine, and so the doublet, each of the doublet that was obtained at higher temperature will now split into a few more lines because of interaction with the FF, the fluorine. Yeah, so now you consider all these interactions and go on splitting it. So what you will obtain is that each of this, so now the fluorine one is obtained at minus 41 ppm, another, so this one is due to the equatorial. So this entire thing that we are observing is the equatorial, fluorine equatorial, and this entire thing that we are observing is due to the fluorine axial. So you have like splitting pattern you can draw again. So first the interaction with the phosphorus, and then draw the interaction with the fluorines. So that's how you are getting a quartet here, but amongst them the JFF is split by, so this is coming out to be around few. So this is, so remember this J 124 hertz JFF. So coupling constant for the fluorine interaction is on the order of 124, whereas so equatorial and axial, whereas the fluorine is 1048 for the JPF. So interaction, the coupling constant for JPF is 1000, 100, and this is 1000. The scale is very different for two. So you can easily, so splitting, so when you are talking about the axial, there is interaction. So F axial interaction with P. Okay, so you start with F alone, then interaction, so it is much, so it splits into two, right? And because they are very far away, and the splitting that will happen due to, this is due to phosphorus 31p magnetically active. Now in the second case you add P to ho gaya P wala. Now you also think of its interaction with the fluorine which is equatorial, so that will split it to another two, right? But this splitting will be small, JFF. JPF is much bigger, so this you draw here, and then this has to be drawn much smaller. This is the interacting nature of nucleus has changed. First splitting we got due to interaction with phosphorus. The second splitting pattern we are obtaining due to interaction with the fluorine, right? So this one is again JFF of the same type. So this is 124 hertz difference, and this was 1048 hertz. So that's why this is the pattern that you are obtaining, quartet here. And similar thing you can apply for the other. So here, in case if we change it to think of the, instead of axial we take the equatorial one, then we have to consider one by one. So we get this thing. So just a moment. Equatorial one is now interacting with axial. So how many axial? You have two axial fluorines, so there will be one more thing. So in addition to this, you will have, do you understand what we are doing? Do you understand it? So this is still JFF, but we are considering this equatorial F equatorial with the second axial number 1, P से हो गया interaction FAX1, and then we are considering FAX number 2. Number 1 हो चुका, so that's why 1:2:1. So you are getting one triplet, another triplet, so two set of triplets that appears there, like this. So the pattern is very clear why you are obtaining this kind of pattern in PCl2F3. Okay, so it is so this is what you obtain. So to summarize this, at -22 and above, the temperature above -22°, all fluorines are equivalent because of pseudo-rotation, and only a doublet will be obtained in NMR signal, 19F NMR spectrum. However, if you reduce the temperature to -43, the pseudo-rotation stops, and you will obtain two sets of peak at this position and this position. So you basically you call it a quartet here, quartet and a sextet. The two triplets you see separated by a farther will be one. We have already considered the coupling with phosphorus, and that is giving us 1048. So this is PJPF, like this. Okay, so we have done this. So this was my target to do this part. This is very important because mostly in many of the exams you will be asked this kind of questions about splitting patterns that you obtain in NMR or EPR. One more important aspect that I would like to cover in today's class is on regarding the solvents that we take and why we use such solvents. So that is so typically you will find that yeah, for NMR spectroscopy the solvents taken are most of them are like deuterated. So hydrogen is replaced by deuterium. Why do we take deuterated solvents? So deuterated means replacement replacement of what replacement of 1H1 with 2H1. So deuterium, this is deuterium. So that is a solvent in which 1H1, the hydrogen atom has been replaced with deuterium, is called a deuterated solvent. And typically you will find that in the whenever modern spectrometers which are pulsed NMR, which are FTNMR, they you typically need this kind of deuterated solvent which are expensive. So you have to so sometimes you will find that it is CHCl3 in this CTCl3. So this is deuterated. So this is deuterated. Similarly, you'll find many more such examples. Uh, Deuterated acetone, deuterated benzene. So that is a process of replacing the hydrogen with deuterium, and this is typically done for NMR things. So this is something that we need to understand why we do this, because you don't want the solvent signal to dominate. So one thing, if you are performing proton NMR, suppose, and you are having water or any other thing as solvent, you will have so much signal coming from the protons, the 1H nuclei of the solvent itself, and that number that's huge. The solvent are always much in larger amount than the solute, and they will dominate the spectrum. You will not be able to see the solute spectrum because the signal will be so high for them. And so in 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 that context you will have huge interference of the due to the absorption by the solvent, and will not be able to see the actual thing. So because normally if we the solutions that we take, you have this ratio. The solvent molecules are 1,000 times more than the solute, and so 1,000 times. So if they are magnetically active, the proton is there, H1H nucleus is there in that solvent, which is outnumbering by 1,000 times more, then you will be getting that huge signal. So that is what you have to avoid, and to avoid that, it is better that if I have to record proton NMRs, 1H NMR, I will take a I will my choice will be something, a solvent which does not have hydrogen at all. So carbon tetrachloride CCl4 is preferred, ideal one, but there is a problem. CCl4 is having no hydrogen atom, so that's a good thing. But there is a problem of solubility of many compounds, and that is why its limitation is there. It is not much used. So, but in order to avoid this problem, what we do, we use organic solvents like CHCl3, in which H has been replaced by deuterium. So that kind of thing is done. Most commonly used solvents are deuterated chloroform, deuterated benzene, deuterated acetone. So this kind of things are normally used. or deuterated dimethyl sulfoxide, DMSO deuterated, that is also. So these are the solvents that is most commonly used for NMR spectroscopy, particularly in pulse NMR. These are things that you will need. The other reason that I would like to point out is that yeah, magnetic field strength. So usually the superconducting magnet that is being used has a tendency to drift. The magnetic strength slightly gets reduced. Uh, it drifts from its original value with the passage of time. So you need to correct that by applying more current or something. You have to adjust that to keep at the same strength magnetic field. Stabilize this magnet. You need to stabilize the magnetic field. So what we do, that this deuterium absorption of the solvent is used as a marker, that we have to keep it somewhere where the absorption for deuterium occurs. You keep the field, adjust the field accordingly, bring it in resonance and keep it there. Okay, so that's a thing. So, and then to define the 0 ppm. So the deuterium frequency and TMS, the difference between TMS is well known. So you do not actually need to have TMS in your system. So that deuterium frequency is used as a reference point, and so you lock onto that signal. You just keep that addition of TMS is not required, and this locking is field. This is also called frequency lock or field lock uh, in the spectroscopic sense. We can use another. We could have used another nuclei such as 19F for the same thing, same purpose, but 19, so it further increases your expenses. So it is more convenient to have a deuterium, is most convenient to having this kind of situation. So these are the reasons why you have NMR. I will also like add one more thing, that many times you will get answers on internet which are wrong. So do not fall in that trap, because if you look for this, if you Google it out, many people will tell you that in the internet you will find people saying as deuterium is not magnetically active. That is factually incorrect. We have seen the deuterium is magnetically active, but its frequency is lying very different from the signal of 1H, and so it is not, because it is not appearing at the same position, it is not interfering with 1H signal which is in my solute. Okay, so many times in internet people say that this is uh, we have seen in early classes. I told you that deuterium is magnetically active. I can show you the chart where we have actually compared. You have one proton, one neutron. So so the spin is not compensated. When you pairing is done, it is proton proton or neutron. If you look at the nuclear shell structure, the sharing is when we talk about spin pairing in nucleus, it is proton with protons and neutrons with another neutron, not neutron with protons. So it is wrong to say that uh, it is not magnetically active. It is wrong. So if you come across any such answer on the internet or some very ordinary books, that is wrong. So look at this. Deuterium is magnetically active. It is a spin 1 nucleus. So to say that deuterium is not magnetically active is factually incorrect, and avoid writing such answers. ठीक है? If you are asked why you use deuterium, do not say, mark my word, do not say deuterium is magnetically inactive. No, it is magnetically active. It has a spin quantum number as 1, G factor, magnetogyrometry, everything. Frequency is also defined. It will appear at a different frequency. So proton 1 appears at 42.576 megahertz, a deuterium will appear at 6.5 megahertz. So you your so it is removed from the proton site, in the chemical shift scale, and you can easily see this. If there is a 1H nucleus proton is present in the solute, you will get the signal without interference with the solvent signal. That's the idea. Okay, and anyway you compare this odd number. So if you deuterium, it is odd number of proton, odd number of proton, neutron, so it should be like this. So by any consideration you cannot say that deuterium is magnetically not inactive. So in fact, I would like to show some such in inherent discrepancies which are there on many such sites. So like, see this example. Somebody is asking, this is a good reputed research get not an interactive site, for anybody can make your profile and ask questions. They can share their research. So this question was asked, why it is necessary to use deuterated solvent for NMR experiments, and see what people are answering. And if you followed something like this, then you will be so you have to avoid uh, such things. So like this, see the answer, this particular answer, this gentleman whose profile says that he is a senior professor, he is answering it as deuterium is non-magnetically active, which will not give rise to NMR signals. This is factually incorrect. Factually incorrect. And this answer is given as last year, or this is factually incorrect. Avoid such answers. You can see another statement like this, Pratika Gavas. So you can see line by line their answers are matching in their wordings also. Deuterium is non-magnetic. So this is incorrect. Okay, you apply your own sense of whatever science you have learned. You apply your own logic and then come to a conclusion. Do not go for such books which tell you, because I definitely think that they are referring to certain books, and that's why their line by line their answers are similar, right? So I don't know which book is writing this, but this reason is wrong. Deuterium is non-magnetic. No, it is magnetic. It is. It is. It has a spin 1. It is a boson. Okay. So avoid such things in your answers. Be smart. Okay. So that's all for today. Thank you.